with the sources of magnetic field, chapter 28. And we found that the sources are moving charges or currents. And we use the Biot-Savart law to integrate to find out what the magnetic field is. And we've already found out what the magnetic field is from a long straight wire. The magnetic field produced by a long straight wire is equal to mu naught I divided by 2 pi r, where mu naught is the constant, the magnetic susceptibility of free space. Mu naught is defined in such a way that it is exactly 4 pi times 10 to the negative 7 Tesla meter per ampere. And along with this definition, we define the amount of the current of 1 ampere. So in other words, it's within the definition of the ampere, which is a strange definition. It's if you have 2 parallel wires carrying a current of 1 ampere, they will have a force per unit length of 2 times 10 to the negative 7 newtons per meter. That's how we define an ampere. The coulomb then is defined as 1 ampere multiplied by 1 second. How much charge passes from an ampere flowing in a second. And that's why the coulomb ended up being such a weird in terms of the electron charge. Because we defined it in terms of the current ampere. In other words, we defined the ampere first and then everything else kind of followed. So just kind of understand that's why it's all weird. Okay, so when 1 ampere flows, the force per unit length is 2 times 10 to the negative 7. Strange, but we can also talk about the magnetic field created by a circular loop and what that looks like. So let's say that we have a circular loop of current carrying current I with a radius r. And we're looking along the axis of the center. And we're going to define the central axis as being a distance x away. So the point that we're going to look at is a distance x away. And so in this case, if I looked at the direction of the magnetic field at each point here, it would be draw that r vector. So I would draw like a little piece of current, my dl. So let's say my dl is up right here. And then I would draw my r vector right there. So I hat cross r hat is going to be pointed in some odd perpendicular direction, kind of like this. This would be my dB. It would be perpendicular to r hat there. dB vector. Now the thing is, as I go around the cone of the circle, the dBs would make a cone, because all these points would be perpendicular. So it'd make a cone around this area here. So in other words, if I put my R from the bottom, I'd make another dB. And so it would turn out and make a cone kind of around in this region here. So the cones of dBs. The cones of dBs. So what happens is that the planar vectors of those cones, of that cone. I wish I had a cone with me. Here's what the dB does, okay? The dB does this. So my current loop is here, down here, okay? Up here, my dB from each point of that is going to do this. Go around in a circle like this. That's what it's going to do as I go around the circle down there, as I integrate. My dBs are going to go around like this. So when I add all of these dBs up, notice that all of the components in this direction are going to cancel. So in other words, this one's going to cancel this way, this one's going to cancel that way, that one's going to cancel this way, etc. But all of the ones pointing away from the loop, they're all going to add. So the ones pointing away from the loop are all going to add. The ones pointing in the plane of the loop are going to cancel. So you only end up with the total component along the axis itself. Total component along the axis itself. So what happens here is that we then do the B perpendicular, and we solve for what we call B perpendicular, which is the magnetic field that's perpendicular to the plane of the current. Perpendicular to the plane of the current. So B perp is equal to, after you do the integration, you don't have to worry about it, mu naught I A squared divided by, where A, by the way, is the radius. They said it was A. Divided by 2 x squared plus A squared to the 1/2 power. No, 3/2. My eyes are messing me up. At least my knowledge of physics didn't, because I knew that 1/2 had to be wrong because it wouldn't come up with the right units. 3/2, that comes up with the right units. All right. We can now, in terms of direction. Your textbook actually gives you a different right-hand rule than the one that I used when I was in school. But the thing is that it works for circular loops and it works for the inside of circular loops. What the magnetic field actually does is that, remember, it's going to curl around the current. It's going to curl around the current. So if I look at a loop, so I'm going to have a loop. I'm going to try a 3-dimensional drawing of the current loop here. Okay, so here's my current loop. Okay? If I put my thumb in the direction of that current, notice that the magnetic field is going to curl around it. So if I draw it, it's going to draw like this. It's going to curl, it's going to come out here and in here. So it's going to curl around that loop. So on the outside of the loop, so if I draw it over here on the side, I'll draw a bigger line so you can kind of see what's going on. So on the outside of the loop, on the inside of the loop, it's going to go up here in the center, because I'm pointing my thumb here. And on the outside, it's going to loop back down like this. It's going to loop back down like this. There are so many situations, though, in which we will want to know just the magnetic field on the inside of that loop, where we will just want to know what the magnetic field inside of the loop. And there's a shortcut. So in other words, this one is put your thumb in the direction of the current and your fingers. Okay, that is the worst looking hand I've seen. This is your thumb, it's in the direction of the current, and these are your fingers curling in the direction of the magnetic field. Okay, so the thumb is in the direction of the current, and your fingers are curling in the direction of the magnetic field. I mean, that's the way we do it with a long straight line, and that's the way that it's kind of defined. But there is a simpler trick to figuring out what the magnetic field is doing on the inside of a current loop. And that is, and this is the one they show you in your book. Take your fingers, put them in the direction of the current. Your thumb is going to point in the direction of the magnetic field. then just remember on the outside, it loops back around. So the simpler way to do this is to put your fingers, curl fingers in the direction of the current, and your thumb is going to point in the direction of the magnetic field inside of the loop.
It's not hard.
Huh? So notice in the inside of the loop, it's going to be going up.
Switch hands.
No, I didn't. There it is. This is a perspective drawing. That's actually going into the page here. The thumb is going into the page.
Okay.
Because it's over here. If you're over here, your thumb's going to come out of the page. And your fingers are going to curl like this.
But why? Can you just demonstrate the bottom one without the drawing?
Demonstrate what to do on the bottom without the drawing?
Yeah.
Yes, okay. Take your right hand. So this is the trick to find out the magnetic field in the middle. Okay? Take your fingers, curl it in the direction of the current. Your thumb is going to point in the direction of the magnetic field. Okay? So that's the magnetic field in the center. Okay? And it's just much simpler to remember that than to try to do this all around the circle. Just kind of see what's going on the inside and the outside. Okay? One of the older professors asked me about it. Did I teach them that? And I said, yes. Even though it wasn't in their old textbook, I used to teach this all the time. And I said, because, and then he said, oh, he was just like, oh my goodness, we used to, I said, I told him it wasn't because of my genius that I taught it this way. It was because I gave up trying to teach this. Because this is very confusing sometimes. You could just do this, it's quick and dirty. There you go. Quick and dirty. Okay, so there's the magnetic field from a current loop, and this is on the axis of that current loop. And so notice that if we take our, let me do it for this drawing here, if we take our fingers, point them in the direction of the current, the thumb is pointing this way. So that's why I know my B field here is going to be away from that loop. On this side. All right. Well, now we want to know a fancy way to exploit symmetry and calculate magnetic fields. This is what we did with electric fields. If you remember, we had our electric fields and we integrated over to try to get the electric field from like a finite length of a line charge and things like that. And then we went on to Gauss's law to exploit symmetries. And Gauss's law for electricity was that the integral of E dot dA was equal to the amount of charge enclosed inside of the Gaussian surface divided by epsilon dot. Okay, so we had that integral. And so what we want to do is we want to do a similar thing for magnetism. A similar thing for magnetism. We have an integral of B dot dA is equal to, oh wait, we already discussed this. Magnetic field lines are loops. Therefore, there's no beginning part and no end part. If I do a surface integral over this, I'm at 0. Well, that's not going to work. We need to do something else. The surface integral fails to try to find out what magnetic field is. Okay? Well, there are the other type of integrals. Instead of a surface integral, we can do a line integral. Now, I introduced this back when we talked about Kirchhoff's law, because the voltage is a line integral along the electric field. Remember, the voltage is integral from A to B of E dot dL, where dL is the line integral. This is the voltage difference. But if you loop back onto the same point, you should get 0 because the voltage is single valued. So we have our line integral for the electric field. That's 0. I'm going to put a little asterisk up here.
Since we're going all around the circle, we probably want to go semicircle, I guess, on the diameter for the magnetic field.
Well, what we want to do is we want to try this for the magnetic field and see what happens. Okay? So let's try it for the magnetic field. Let's try this for the magnetic field and see what happens. Okay?
Is this the same chapter?
This is the same chapter.
20.
Yeah, it's the same chapter. This is kind of the review I'm leading into this last equation we're going to come up with.
Okay.
All we have to do then is fix them after this. There's a couple that we need fixing after. This is one of them. Okay? So let's try to look at this. B dot dl. Integral of B dot dl. So what I'm going to do is I'm going to take a long straight wire. Because we already know what the magnetic field is around a long straight wire. And I'm going to integrate around this loop. That's going to be my loop. So I'm going to choose a circular loop of radius r centered at the current. And the reason why I'm going to choose that for my test integral is because I already know what the magnetic field is from a long straight wire. We got that from Biot-Savart. Sorry, it's Biot-Savart. I'm supposed to pronounce the T. I just always call it Biot-Savart. It doesn't matter. He's dead. Doesn't care what we call him. Okay? BS. Biot-Savart. That's what maybe that. He might turn it pretty straight. All right, so we're going to put our little DL here. So here's our little DL. Okay? The magnetic field of this point goes along this line here. And we know the magnetic field is mu naught current divided by 2 pi r. And now I want to set up my integral. Okay? So I want to integrate around this thing of B dot dl. Well, in this case, the B is the same at all points. And it's equal to mu naught I over 2 pi r. Okay? Dotted with the dl. So the vector dotted with dl. Now, at all points along this, when I get over here, dl is this way when I go around my circle, but the b is that way too, because the b goes around the circle too. So my b and my dl are always in the same direction at any point along my circle. Since they're in the same direction at any point along my circle, this dot product will always be 1. Same direction, dot product 1. So the dot product is always going to be 1. So I don't need the dot product. My thing is just now an integral of this dot times dl, because the dot product is always 1. The integral is over this path, and r is the same on every point on that path. So that can come out. So can mu naught times I divided by 2 pi. All of that can come out of this. So all of it comes out. And now I just have an integral over the dl in that circle. What's the integral of dl? L, which in this case means the length. The length of what? The length of the circle. So this is just mu naught I over 2 pi r multiplied by L, the length of the circle. What is the length of that circle?
Circumference.
Not the surface.
Circumference.
Circle. Length of the circle. It's the circumference of the circle. Because we're going around the circumference. So that's the length. And so the circumference is 2 pi r. So this is mu naught I over 2 pi r times 2 pi r. And that's equal mu naught times I. And the other important thing about this is that what it is not, in other words, we can use this because it's not something. We can't use this because this integral is equal to something.
Is something 0?
The something is 0. In other words, if this ended up being 0, we couldn't use that either because there's no way to know. But it's not 0. It's not 0. Now, Ampere's law generalizes this to all magnetic fields and all currents. And I could have done a fancy derivation, but none of you have vector calculus yet, and so therefore I'm not going to do it. I forgot what it was anyway, because it's been forever since I've looked at the derivation of Ampere's law using the Biot-Savart integral blah blah blah. Get it? What it turns out to be is this. The integral B dot dl is equal to mu naught times I enclosed. Mu naught multiplied by the I enclosed. Now, this law does not restrict the line integral to a planar shape. However, in this course, I will confine all line integrals to some planar shape. And they're like a circle or a square or a triangle or whatever. That way, this is much easier to define for you to see. Okay? So in other words, what the mu naught I enclosed means is the amount of current that penetrates that circle or goes through that shape. So if I took the long straight wire, so this is a long straight wire with current, say, coming out of the page, and I integrated with a current I1, and I integrated around this square, okay? The total integral around that square, because, and then I'll put I2 over here, going into the page, I2, going into the page. The integral around that square will be mu naught multiplied by I1. I2 is not included because I2 is not enclosed. I2 does not go through the shape in question. I2 does not go through the shape in question. So this would just be the integral around the path. I don't know, call it, oh, wait a minute. Let's say that this is a square. This is a square that's centered on I1, with each side having length A. Okay? And I want to know is what is, and I'll put point A and point B here, the integral from A to B of B dot dl. Ooh, now I'm getting tricky. I love questions like this on a test too. They're great for multiple choice. Because if you get it, you get it. If you don't, you don't. So I'll throw this at you now. Okay? Let's exploit some symmetry. I know that the integral around the whole square of B dot dl will be what? Integral around the closed loop B dot dl is equal to mu naught multiplied by the I enclosed, which is I1. So now what would this be?
Divided by 4.
Divided by 4. Because it's 1/4 of the way. Exploit the symmetry. Because this is symmetric, and this is right in the middle of it, I know that each one of these lines would have the same result. Would have the same result here. So I know that one of them just has to be this thing divided by 4. Mu naught I1 over 4. Cool, huh? Exploit that symmetry when you can. Yes?
So the length is always related to the diameter or circumference of the shape?
Yeah, basically, along DL, you're going along the outside. We can't exploit it. You wouldn't want to do that, It turns out to be a mess if you really try to do that physically with integration. But yes, DL goes along the outside.
Would you ever do one where half of it is enclosed?
Hold on. There's different configurations we're going to look at now. Where this law works. Okay? All right, the first thing we're going to do is we're going to do a long straight wire, except for this time we're going to take a look at both the inside of that wire and the outside. Inside and outside of a long straight wire. So I have a long straight wire. I'm going to draw it big here. Big, fat, long straight wire. Even if it may not be big and fat, I don't know how big it is. Okay? And let's say that this wire has a radius r, and I'm going to make that radius capital R. So the radius of my wire is capital R. And that wire has a uniform current coming out of the page. So I naught is distributed uniformly out of the page. And I don't want to call it I naught. Well, I guess I should call it I naught. I naught. So I naught distributed uniformly. It doesn't necessarily have to be distributed uniformly, but it always must have the radial symmetry. In other words, the angle here, if the angle here mattered, like if the current here were different from the current over here, we'd be in trouble. We couldn't use Ampere's law because we need that symmetry, that radial symmetry, so that all the way around the circle, no matter what you do, all the way around the circle, your current would be this, the density of current or the way the distribution of the current should look the same. Because we have to exploit that circular symmetry. So now, instead of drawing a Gaussian sphere, we draw what we call an Ampere loop, if you will. So I'm going to draw an Ampere loop centered around the middle of this. So here's my Ampere loop. Okay? My Ampere loop has the radius of little r. It's my Ampere loop. Now this whole thing is coming out of the page here. All right, so let's write down Ampere's law. Ampere's law says that the integral around that closed loop of B dot dl is equal to mu naught times the I enclosed, the current enclosed. So now here's how we exploit this symmetry. I could go around the loop either direction, clockwise or counterclockwise. So we just want to know, make sure in the cases when you do all of these, just go ahead and do it in the direction of the magnetic field. Just do it in the direction of the magnetic field. So you're going DL along there. That way you don't have to multiply minus and get a plus magnitude. So if we're at a point on this thing, and I'm going to put the point up here, okay? So I'm going to draw my little DL here. That's my little DL. So at that point, what's the direction of the magnetic field? Well, the current, all of this is coming out of the page, okay? And you do need to be told that. Out of page. You do need to be told whether it's coming out or in. Okay, so take your thumb, pointing in the direction of the current, coming out of the page. The magnetic field is going to loop around that. So therefore, up there, when you get up to that top point, which way is it pointing? Pointing to the left. Or you could also see that as you continue to go around, the B is counterclockwise around the circle. So the magnetic field up here points in the direction of my DL and is counterclockwise around that circle. Now, because of the symmetry, that the current on doesn't depend on this angle here, the magnetic field here is going to be the same as the magnetic field here, it's going to be the same as the magnetic field here, it's going to be the same as the magnetic field here. In other words, no matter where you go, if you dance around the current maypole, the maypole of current, okay, it will always look the same. So therefore, the magnetic field is going to be the same at all those points. I don't know what it is, but it's going to be the same all the way around. The dot product is always going to be 1 all the way around. So once again, just like what happened with the Gauss's law, for Ampere's law, the B, we're always going to make this thing so that the B comes out of that integral. You can't solve for a B that won't come out of the integral. The B has to come out. Or part of it has to be 0. So the B comes out of the integral. Dot product is 1. And so in this case, I just get an integral over my DL. Integral over DL is just the circumference of that circle. The circumference of that circle is 2 pi r.
Well, B is 2 pi big R, right? Long.
No.
No.
We're finding out what B is. We don't know what B is. We don't know what B is in this case. We're inside of that wire. Outside of the wire, mu naught I over 2 pi, mu naught I naught over 2 pi times whatever the radius is from the center. So in other words, outside of a wire, it looks just like a thin wire. You know, it looks just like a thin wire. It's just like, remembering Gauss's law, outside of a spherically symmetric charge, looks like a point. Yes?
Does I not include I enclosed, or is there different?
No, I enclosed is different because notice we didn't enclose it all. So now what we have to do is we have to figure out how much current we enclosed so we can plug that in. So our next step is to try to figure out what this I enclosed is. Okay, so I'm going to bring up another piece of paper to look at what I enclosed is. All right, since it's distributed uniformly, when we talk about current being distributed uniformly, we're talking about the current density being the same at all points. So the current density is the same at all points. So what is the current density? Current density is defined as being what? Over, what'd you say? Area. Current over area. And that's the same at all points throughout this thing. So the current density here is my current I naught divided by the area of what? Which circle? The big R circle. Because the I naught is distributed over the whole thing. So this is pi times big R squared. Now the current that is enclosed is equal to our current density. Since it's uniform, it is equal to the current density multiplied by the area that is enclosed. Well, what's the area enclosed? Pi times
R, little
little r squared. I can then plug in for J. And I can do some cancellation here. So what I get is I get that the I enclosed is equal to I naught multiplied by little r squared divided by big R squared. We can make a check of this, by the way. We can do a check for this. Because if you go back over here, if my little r is at the edge of this, if my little r is equal to capital R, what should I have for my current enclosed?
I know.
I naught, all of it. And if you plug in big R squared divided by little r squared, I get I naught for my current enclosed. So indeed it does check. The other check is if R is equal to 0, this should be 0 because I'm not enclosing anything in a R equals 0. I don't enclose anything in anything. R equals 0, so that should be 0, and indeed it is. So at least the limits are correct. Okay. In this case, if you remember how this ended up working for volumes back when we were doing Gauss's law for the spheres, this would be r cubed over capital R cubed. That's what that would turn out to be for those spheres, because it was a ratio of volumes. This is not a ratio of volumes, it's a ratio of areas, because the current density is defined as being the current per area. And we're doing a line integral, not a surface integral. So that's why it's a ratio of squares. By the way, this will only work for the uniform distribution of current density. Okay, so let's do this. So we put this in. 2 pi r equals mu naught, I naught, multiplied by r squared over capital R squared, divide by 2 pi r, and I get that the magnetic field inside is equal to mu naught I naught r divided by 2 pi capital R squared. So if I were to look at the way that this current is, this is going to be my capital R. Inside of the thing, it increases what? Well, if I have r to the what power here? First power, 1. So what does that mean in terms of what's going to happen in here? The dependence on r. So then it's a first power. What am I going to draw? A line. There we go. I'm going to draw a line. It's a straight line. You guys need some coffee this morning. I probably need some more too, but it's a straight line. The first power of r is just straight. It starts up here, increases linearly. There it is. Once it gets outside, it looks like this. Outside, And you could also show this using Ampere's law, because you end up enclosing the whole thing. So I naught is what is enclosed. So it's mu naught I naught divided by 2 pi r. So then it goes down as a 1 over r function. And so the maximum magnetic field you get is right at the surface. That amount is, I'll just put B max. And in this case, B max is equal to mu naught I naught over 2 pi capital R.
When you say outside,
Outside of the cable. Outside the cable. I should be able to leave this alone and did not go off on it. All right, applications of Ampere's law. We went over one. Is that center uniform distributed? Next. Is the magnetic field from a solenoid. Magnetic field from a solenoid. A solenoid is a tightly wound I guess cylinder or current in a cylinder. Okay? And I'm going to draw this kind of loosely winding, and I need to make sure that I do want to be consistent with what the book is doing. Yes, the book is. All right, so I'm going to draw the solenoid. It looks like this. The solenoids you work with are much more tightly done than this. This wouldn't work. This would not be a solenoid. It would be kind of an individual thing that you'd have to, kind of play around with. And I run current through here. And what we want to do is we want to look at the magnetic field. We want to look at the magnetic field generated, especially in the middle of that solenoid. And your book got cute. Okay, so we've got tightly wound paths here. At the top of the page is going into the paper, and at the bottom of the page is coming out of the paper. So I'm just going to draw those circles down here for the solenoid. So in other words, my solenoid has at the top of the paper lines. Now I'm going to put these close together. And at the bottom, we've got them coming out. All right, now what I want to see is what happens with the magnetic field. What happens with the magnetic field contributions from kind of this top piece and the bottom piece. Now this isn't a great derivation here, but this will just kind of give us an idea of what's going on. Because remember, this thing is round. This goes all the way around. So in other words, we've got some in the back and some in the front and some on the sides and everything else. For the loops that are going into the page, if you put your thumb in the direction of those X's, which would be into the page, notice that around those X's, you're going to have a clockwise currents, clockwise magnetic fields. Okay? So here we're going to have clockwise magnetic fields. me draw one here. Okay? So here's my magnetic field. It goes clockwise around this thing. Okay? For the ones on the bottom, I'm going to have counterclockwise magnetic fields. So in other words, my magnetic fields on the bottom are going to point counterclockwise around these. Counterclockwise around the ones on the bottom. Let me draw those with the yellow. Let me draw those with the yellow. Okay? Now I'm going to draw this one, this size here, and then I'm going to do this with this one here. I want to take one over here. I'm going to draw it, I'm going to draw one like this, and I'm going to draw one like this. There we go. Well, actually, I should have centered it on there, but I didn't, but you'll get the idea. Okay. Now, if we look at what happens with this magnetic field, notice on the inside, when I go clockwise around this one and counterclockwise around the bottom ones, notice that in the middle of this solenoid, they add up. In the middle of the solenoid, they're going to add up to each other. On the outside, though, when I go counterclockwise around one and clockwise around the other, on the outsides, they're going to cancel out. If these are packed close tightly enough together, there will be an essentially very, very little field leaking out of the solenoid itself. And so what you get is you get a situation where the magnetic field is mainly contained on the inside of the solenoid. On the inside of the solenoid. And outside of the solenoid, it is virtually zero. There's some leakage because, of course, we can't make infinitely long solenoids. We can't pack them infinitely tight. But if we could, then it would be true cancellation. There would be no magnetic field on the outside. All the magnetic field would be on the inside. But for the most part, this works. That's why if you notice, there's lots of things with solenoids. There's lots of, when we start wrapping a bunch of coils around really tight like this, a bunch of shapes we do that with. Okay? So here we do this. All right, so let me go down here, and let me draw this a little bit more spread out now. Okay, so one. I'm going to draw it a little bit more spread out. But do remember that these are actually tightly close packed together, blah, blah, blah. And I'm going to do out. Okay, so now what I want to do is I want to use Ampere's law to try to figure out what the magnetic field is. What the magnetic field is. Okay? What the magnetic field is on the inside here. So remember that this region, this is the inside of the solenoid, and then everything else is on the outside. Okay? All right, so my magnetic Ampere loop could be any shape. It doesn't have to be a circle. But I need to include some current. I don't want to do both sides of this thing because then the current at the top would cancel the current at the bottom. In other words, current going out of an Ampere loop would cancel current going into an Ampere loop. So I just want to include one side or the other, so let's include the top. So here I'm including the top. Here we go. Ta-da! All right, so I include so many of these. And so my thing is going to have a length L and a width D. Okay? And I want to integrate in the direction of the magnetic field, so I'm going to integrate clockwise here. Because my magnetic field on the inside is going to be clockwise. All right, so here's my, oh, whoops, I don't want to use L here. Because I used little l in my D, and change to a B. Actually, sorry. Capital L, how about that? Capital L. Sorry, everybody, capital L. All right, now, let's write down Ampere's law. So I got the integral of B dot dl equals mu naught times I enclosed. Okay, mu naught I enclosed. So let's work on this side first. Now in this case, the magnetic field in different regions is different. So when I integrate around the loop, I have 4 regions in which I'm going to integrate. I want to integrate on the inside of B dot dl. I want to integrate along the left B dot dl and the right of B dot dl. And there's a reason why I wrote the left and the right together, because I'm going to treat them together. I'm going to treat them together. And then the integral to the top, or the outside, B dot dl. Sorry for not making lines instead of arrows. All right, so let's go for this. All right, if we take a look at this left one, there's a couple things that happen. Let's see, the magnetic field in this is this way. The magnetic field on the inside is this way. The dl here is along this direction. So here this dot product perpendicular, so therefore 0. And once I get to the outside, there's no magnetic field anyway. So both of these are 0 because B perpendicular to dl at all points on those paths. B is perpendicular. And over here, it's B and dl is coming down this way, but that's still perpendicular. That's still perpendicular. So therefore, it's B is perpendicular. So those two go away. The one up here goes away in our ideal solenoid, because in an ideal solenoid, which really can't be made, but hey, ideal solenoid, what's happening up here? The magnetic fields cancel and the magnetic field itself is 0. So up there, there's no magnetic field. And if I really wanted to get cute like your textbook does, textbook really gets cute about this. What they do is they extend this like to infinity, so then you're sure that the magnetic field is 0. Okay. You get the same deal because, of course, these perpendicular lines anyway. So we just go far enough away, and it's far enough away from the solenoid, you get 0 as well. Just you stay these perpendicular lines, go to the edge of the known universe, and there you go. So this is 0 because B itself is 0. So then that's going to be 0. So what we're left with is this integral over this line on the inside. Now the inside of this, if it's long enough, this is why we say it's a long solenoid, that there's no difference between this point and this point. If you look at your financial aid line and you walk up 2 spots, it doesn't look any different because it's infinitely long line. So the magnetic field here is going to be the same as the magnetic field here. So the magnetic field inside of this is going to be equal at these points. So we can pull that out. It's also parallel to dl at all points. So here's my B, my dl is parallel. So this then comes out. So I got my integral here. I'll go back to this one here, because I want to write an equation down there. Okay, so this becomes the integral from the inside of B dot dl equals mu naught I enclosed. The B is parallel to dl, so we just end up having the integral over this path on the inside of dl. This is the length of that path. What is the length of that path? L is the length of that path. So we got B L equals mu naught I enclosed. Well, in this case, it would be what? if I said that this was I naught, right? That's I naught is what's going through the solenoid. Or I'll say I naught, just because I naught is what's going through the solenoid. All right? Then this would be how much is going through the loop. If I naught is the current going through the solenoid, how much is going through the loop in this particular loop that I've drawn? No? Okay, I naught is the current running through the solenoid. How much is going through the particular loop that I've drawn?
Cylinder length divided by the length of the loop that you chose.
No. Huh?
What were your lengths?
No here. No.
Oh, wait, are you asking?
BL
it's gonna be the
divided
same.
by
I want to know how much current is going through that loop that I've drawn.
Oh, it's gonna be the same.
BL divided by mu naught.
No.
Wouldn't it be the same?
No. Not I naught. It's got to be a current. It's not I naught.
Is it a fraction?
Well, let's see how much. Let's see. Well, let's see. Each one of these is I naught going through there, right? So here's my loop. Let's see how many go through. A 1, a 2, 3, 4. 4. The I naught that's going through there is 4 I naught. I've got 4 of these going in there. I've drawn this loop. I got 4. 4 I naught goes through. That's how much is going through the loop. Just look, 1, 2, 3, 4. There it is. Each one of those is I naught.
Okay.
Yeah. 1, 2, 3, 4. I know. Now that might confuse you because it seems completely arbitrary how I drew the picture. And that's true. It is completely arbitrary how I drew the picture. That's why I said in this particular picture, I've got 4 of them. It's completely arbitrary. So since it's arbitrary, I'm going to call it n because I don't know what it is. It's how many I included in my loop. If I draw the picture differently, I would include a different number, right? Specifically with this one, if I'd drawn it bigger, I would have included 5 or 6, maybe 7. Or if I drew it longer, I could have included more. Or if I drew this shorter, I might have only included one of them. I don't know. So it's just some number in. Because I really don't know. It is completely arbitrary. I asked a very simple question, but it was so confusing because it's kind of counterintuitive that you know, this drawing is 4, but it's completely arbitrary. And you're thinking, that can't go in a thing. It's completely arbitrary. So this is just n times I naught. I don't know. N times I naught. Well, of course, I have a problem with this. I've got not 1 but 2 arbitrary things in here. Because the ampere loop is a theoretical thing that I've drawn. It doesn't really exist. There's no physical ampere loop stuck in space somewhere that you draw. It's completely arbitrary. So this L, that dimension, is arbitrary. And then so is the number of loops that I happen to have enclosed. When we solve for the magnetic field here, we get this. Mu naught, and I'll just say I is the current going through there. I naught's a nice number to derive things with, but I'll just go ahead and switch to I. N over L. Aha. Now I've got something. Because notice that the number of loops I include is going to depend on the length of that loop that I draw. The bigger the loop, the bigger the n. This ratio represents how tightly packed those loops are. How tightly packed those loops are. And so what we do is we just say, we define a kind of a loop density, if you will. Call that little n, where little n is the number of loops per unit length. So it depends on how tightly packed my solenoid is, how close together those loops are.
Is n a subscript?
What, this n?
Yeah.
No, it's just n. It's defined as being n over L, number of loops divided by the length. And since these two numbers are completely arbitrary, this one is not. It defines how tightly wound your solenoid is. So that's why you'll see solenoids wrapped around. And then sometimes you'll see loops on top of loops like this to get more loops per length. Because the more loops per length you get, the stronger the magnetic field in the middle. Solid.
Cousin,
Yes?
can you go one more time about why the integral and out is 0?
The outside integral is 0? Two ways to think about this. Because what happens is there's cancellation from this bottom half and the top half on the outside of the solenoid. So in other words, the currents that are coming, so in other words, when you think of a solenoid, you want to think of like a currents going like this. Kind of flat sheets of current, if you will, because you've got all those loops tightly packed together. So you've kind of got current doing this. And so the magnetic field from what's going on up here on the outside of the loop is going to cancel with the magnetic field that's happening down here. So you've got the thing on the top and the outside. But inside they add up. Okay, here's another one. We'll start on this one. And you guys can finish it at your leisure. It is gone over in the book. Okay, it is called the toroid. Toroid. I feel the same. Now, what a toroid is basically a solenoid that's kind of been wrapped into a circle. Solenoid has been wrapped into a circle. So if I were to draw it, it's kind of drawn like this. Kind of like that. Oh, my hair ain't like that. I wish I had hair like that. There wouldn't be any loops if it was me. All right, here we go. So with this one, what you have on the inside, you've got loops, and let me see. Just want to kind of be consistent with what your book is so you can actually look at this. So on the inside, what they have is the loops are going in. On the outside, the current is coming out. Okay, once again, if wrapped tightly enough, there'll be cancellation on the outside. So we don't want to worry about the outside. Well, actually, yeah, there's going to be cancellation on the outside, and we can actually show that. But on the inside, what we want to do is we want to take an ampere loop on the inside of this thing. So the inner radius here, they usually has an inner and outer radius. It shows a nice picture in your television. This is what it really is supposed to look like. See, ooh, nice picture here. Hey, get back here. Ah. Didn't work. Open the picture? Darn, it's not letting me open the picture.
Zoom in.
Zoom in here. Yeah, okay, gotcha, thanks. And so now I should be able to. Wait, where's my thing that let me go over? I don't have all my. my tools here. There we go. All right, there we go. There we go. Let's do something better. There we go. Okay, got it. Yeah, there we are. Great. This. Zoom in some more. Yeah, that's kind of what it looks like. Ta-da. All right. So we have so generally there's an inner radius and an outer radius to this toroid. Okay? When you're on the inside of here, if we go inside of the empty space in between, and I draw an ampere loop, so I'm going to draw 3 different ones here. 3 different ones. The one on the inside here, how much current am I enclosing in that? Oh, that's right, you can't. Aha. Okay, go back over here. When I draw my ampere loop on the inside here, and I'll call it 1, number 1, how much current am I enclosing in that?
0.
0, because it's on the inside. What about when I go to the outside here?
Why not?
So the current I enclosed here, okay, 0, 2.
Why not?
Well, the problem is this. I've got 1, 2, 3, 4, 5, 6, 7, 8, or how many of these coming out, and I've also got the same number up here going in.
It's a 0.
So it's 0 because of the cancellation between what's on the outside and inside. That's also 0. So the third one, the one if we draw in the between the two, we actually do get current enclosed because I'm enclosing those inner currents, but not the outer ones. So now in this case, it's just in multiplied by I, because in this case, we've enclosed every one of them around that loop. So when you physically make a toroid, it depends on the number that you use, the number of them that you use when you wrap them around in a circle. And the length of this is not arbitrary either, because it depends on how far you are away from the center of the toroid. So the length of that circle is 2 pi r. So when you get the b multiplied by 2 pi r multiplied by is equal to mu naught multiplied by ni, what you get is in the region of the toroid itself, inside of the between those currents, you get that the magnetic field is mu naught in I divided by 2 pi r. Notice this magnetic field is not uniform inside of a toroid. Because of the way we bent it around in the circle, it's no longer uniform. It's symmetric along the axis. In other words, as you go around the circle, it looks the same. But as you go from the inside to the outside, it's actually slightly smaller. So like at the inside, the magnetic field is going to be larger. Then it goes to the outside, it gets smaller. And then it jumps to 0 once you go outside the toroid. So this is a non-uniform. If you want uniform, you want a solenoid. That'll give you uniform.
So what are the practical applications of the two devices?
Solenoid I've seen a lot. I haven't seen too many toroids.
Do we keep an arbitrary?
It is not arbitrary. This particular end is in the design of the toroid itself. In other words, you know how many loops you use to wrap it around. Yeah. With the other one, it's how tightly packed you are. But if you know the total number of loops and the total length, then that would be the design. So in other words, if I want a certain magnetic field and I have this length of core that I can use, then I need to wrap it tightly. Okay? I will not be going over magnetic materials. That is 28 section something or another. The last section, magnetic materials, I'm not going to go over that. Sorry to get it one of these days.